My name is Sarah Speight, and I'm a postdoc fellow at Memorial University, working with Steve Piercy and Jacob Hanley. So today I'm looking at some petrogenetic characteristics of VMS-associated felsic, volcanic, and intrusive rocks, and specifically looking at insights from zircon textures and mineral inclusions. So to give an idea of just what we'll talk about today, looking at the project overview, to give an idea of why we're doing this work, the methods and the approach that we're using for data collection, so there's some strategies involved with that. Today I'm focusing only on 2 transects and a few samples from those, so looking at Naranda and the Swayze transects. So I'll show you the sample locations and lithologies, as well as then the meat of it, looking at zircon textures and specifically zircon-hosted mineral inclusions. So I'll also have a couple slides at the end from the work done at St. Mary's University with Priyal Daya, who's a PhD candidate, and Jacob Hanley. So looking at the melt inclusion work that they're doing and an update from that, and then I'll just summarize and look at sort of our next steps. So I've shown this diagram here. So it's a cartoon of a zircon crystal with an abundance of different types of inclusions. And really I'm showing this because I want to give an idea of the sort of more qualitative information that we can get by just observing these inclusions. So for example, we have, so if you encounter oxide mineral inclusions, we can use this as proxies for looking at constraints on oxygen fugacity. Silicate melt inclusions, which is the focus of the St. Mary's work, we can start looking at magma parentage and potential primary metal endowment in those. So it's just to give an idea that there is a lot of information that we can kind of tease out of the zircon studies. So for an overview, so our project is looking, so part of the Metal Earth thematic project, like Ross mentioned. Specifically, our work is looking at felsic, volcanic, and plutonic rocks within the Abitibi Greenstone Belt. So that's highlighted here in the Superior Province. And we're really focusing on evaluating processes responsible for differential VMS endowment and assessing how we can use zircon mineral chemistry, tracer isotopes, so uranium, lead, and lutetium hafnium, as well as the geochron data itself to understand the role of magmatism in VMS endowment. So to look at sort of the workflow, the analytical methods that we start to finish go through, on the right is an image showing CL images of zircons and different analytical spots. So we have like probe data collection spots, as well as our ablation markers for lutetium hafnium, uranium, lead, and trace elements. But we start with, first off, doing the CL imaging because we get a really great view of the internal structures of the zircons, and that helps us specifically target where we're doing our laser ablation and probe data collection. So after CL, we go into doing electron probe microanalysis for internal standardization. So the really helpful thing about our data set is that every spot is connected with a probe location, which then allows us to internally standardize the data for a really robust data set. And then we can go through and do our laser ablation data collection for uranium, lead, and trace elements. So we do that concurrently so that we can tie in situ trace element chemistry with time and the textural context. And then finally looking at a secondary laser ablation data collection for the lutetium hafnium isotopes. So we do that by putting the lutetium hafnium ablation spot over the same trace element and uranium lead, so we again kind of maintain that context throughout the whole data collection process. And so right now our sample set, we've ended choosing samples. We're finalizing data collection here in April, but we have 74 samples across the Abitibi Greenstone Belt, and right now more than 3,000 zircon analyses that represent core and rim analyses. So we'll be looking at the crustal inheritance story with that and the overall zircon mineral chemistry. So jumping into sort of where these are and the zircons themselves, so we have a section of the Abitibi shown here and the Naranda transect location. So we're looking at right now 3 samples shown with these red stars here within the, they're all from the Powell block in the Naranda transect. So we're looking at one felsic intrusion, so it's a tonalite sample, and 2 rhyolites that will show the zircons from. So in jumping into those, because zircon textures are, I guess, my jam now, but across the top we have CL images, and then along the bottom we have the corresponding SEM-BSE images, and the probe spots are marked with the yellow numbers. So we can see different textures right off the bat. You see there's oscillatory zoning that is recorded within the zircon crystals, as well as this more blocky sector zoning that you see with the bright, the contrast between the bright zones and the dark zones. And when we look at the image here on the right, so this is all zircons from the same sample, but you do see sort of rounding of that interior core, so it's suggesting xenocrystic cores. So within just 5 zircon crystals here, there's a lot of variety and inclusions, which are marked here. I'll show you some of the EDS spectra profile from. So what I'm really interested kind of in broadly doing with this information is looking at the mineral inclusions and the corresponding just preliminary SEM EDS spectra for their mineral signatures. So I think hopefully we can convince you of some of these minerals being present. Looking at this one, so it might be hard to see on there, but that's why I've highlighted the elements. So this spot here is number 3, and it's looking at a mineral that's enriched in sodium, potassium, aluminum, silica. So I'm looking at potentially a feldspar. We have other minerals, so in another inclusion area we have here a mineral enriched in iron, magnesium, potassium, sodium, aluminum, silica. And so it is important to note, because of the more qualitative nature of the data of the spectra, is that there is a size issue in that there are very small inclusions, so you might have mixed signals in these spectra, but overall looking at the mineral signatures and what they would represent is kind of the goal. So we have other things like looking at this spot here in this zircon crystal around the kind of in the rim of it included, so you can see it in here, is a signature. It's enriched in calcium, phosphorus, and potentially fluorine and chlorine. So we have potential evidence of an apatite crystal that's been entrapped in a co-crystallizing zircon, and potentially, and this is something that I'd like to investigate further, is the signatures of these apatites, because here we're showing one that's potentially enriched in fluorine and chlorine, but throughout looking at different samples, I also saw apatite that did not show that at all, just more of a clean calcium phosphate signature, some that had a calcium phosphate and fluorine enrichment, but no chlorine. And so there's at least 3 different signatures that I can kind of observe already in the just apatite, like the broad apatite chemistry. And so I think that's worth investigating, because we can then get sulfur information from that. And finally, another mineral potential here. So looking at iron, sodium, enrichment in potassium, aluminum silicate. So we have feldspars, we have apatites, potential micas and amphiboles here. And this is from one sample in the tonalite from one of the Noranda areas. So if I want to look then at the other samples, I mentioned looking at a couple of the rhyolite samples. So these are, again, showing the CL images across the top. These zircons came from 2 rhyolites, and they were all within, like I mentioned, that Powell block. And we have different inclusions here at the core of this zircon grain. And we do see a similar textures. We have oscillatory zoning that's been recorded, as well as that strong sector zoning that was fairly unique in the last images. And so we see that, although we do see a lot more fracturing and sort of these cuspate shapes that you might anticipate seeing in a rhyolite. So looking at the inclusions, so again, we see something here, the inclusion in the center part, which corresponds to one of the bright grains you can see in the BSE image. It's enriched in calcium and phosphate, and there is a small peak of potentially fluorine. So again, we see that similarity. The other, another bright grain here in this center of the zircon is showing enrichment in light rare earth elements. So cerium, neodymium, we have calcium that's just showing up weakly, and phosphorus. So it's not quantitative mineral chemistry. I'm not going to spit out a table and give you values of these elements, but the mineral signatures of what they represent, so xenotime and monazite, and the implications of those co-crystallizing with zircon is really important. And then I mentioned mixed signatures, and I think that's kind of what I'm observing here in this area on the second zircon. There's an inclusion here closer to the rim, and so this spectra showed enrichment in calcium, sodium, potassium, aluminum, silicate, but there's also peaks here in iron and titanium, so you can see potentially there's contamination from a nearby mineral, and when we look at the other section of the inclusion here, it actually is more strongly showing iron titanium oxide signature, so something like ilmenite being recorded here, and potentially that being what contaminated that other analyses. So it's qualitative, but it is going to start to give us some information for primary magmatic conditions. Looking at switching over to more the Swayze transect, which in the Abitibi, we're showing the Swayze transect here. So today, just showing zircons from 2 samples, looking at one felsic intrusion from a porphyry in the north of the Swayze Greenstone Belt, and then looking at a felsic lapilli tuff down in the southern area. So these zircons, I think, right off the bat, are markedly different in their texture and in their CL response. Excuse me. So we have a much darker CL response. We do still see oscillatory zoning. That's a classic zircon feature that we expect to see in magmatic zircons. But we do see evidence of something of a dark core here within these zircons. And it's interesting, even in this zircon, which I will show a blown up image of it in the next slide, but there's sort of a convoluted assimilation texture within the core here. And so if we look at the inclusions, so we have inclusions along this zircon core, they're highlighted here, numbers 1 and 2, and we have enrichment, so we have an iron, magnesium, potassium, aluminosilicate, we have evidence of quartz included within this zircon, so that's really important when we're interested in doing titanium and zircon calculations, to be able to have evidence to confirm our activity of silica and our activity of titanium. It'll just allow us to make that much more accurate temperature calculations. And then finally, over on the right side, we have a potassium aluminum silicate, so a feldspar, K-feldspar, included within the grains. So we start to get an idea of the co-crystallizing phases that were happening at the time of zircon growth. So like I said, zooming in on this grain, and a couple of these grains. So these are all zircons from the same sample, so it's from one of these felsic intrusions, a felsic porphyry in the Swayze area. And so we have here the BSE and the CL images side by side. But if I were to say inheritance and CL response, I think overall the group would probably think of something more similar to this grain here, something with a really bright CL response and bright core. But I think it's worth noting, if we look at, and I'll blow this up again, we have these internal structures. We have a rounded zircon core here, and we have these propagating concentric fractures radiating off of, and they're noted by the red arrows, of the zircon core. And actually, see that you can still see the CL response of this grain here. There's actually, it looks like 3 different sections of the zircon. An internal dark CL response core, an outer growth of that bright CL, and then finally a third domain that is, again, a dark CL response in the zircon. And when we look at that, we see, again, that dark zircon core with these radiating fractures. And so evidence shows that when you do see that kind of texture and those propagating fractures, it suggests that the zircon core was crystallizing at a different depth and pressure than the overgrowth in order to, so you have a difference in pressure, and that then can cause these fractures to radiate off the core. So I think it's interesting that we see that in these 2 grains, which look fairly different, but they're from the same sample, and we can investigate that further, and I'll be looking at the zircon mineral chemistry of those to see how they compare. And finally, probably one of the more interesting zircons that we observed in the Swayze sample is looking at, here again, we've got the CL images and the SEM images, and the inclusions are noted here with the bright numbers. But what was a very interesting, so we have oscillatory zoning and actually a lot of complex internal structures. There's rounding of this core, overgrowths of zircons, and the complicated inclusions. But for this spot up in here, which correlates to this bright grain, the spectra show evidence of iron enrichment, copper enrichment, and sulfur. So it's looking like hopefully we can convince ourselves that there's a grain of chalcopyrite here that's been intergrown with zircon. If we look at the next mineral, which is right beside it within that same domain, it's an iron magnesium aluminosilicate. If we continue and look at the other zircon here, in this felsic lapilli tuff, it's an iron titanium mineral, potentially an iron titanium oxide contaminated with a bit of alumina and silicate. But these can then be investigated further on the probe to really get their chemistry solidified. And then finally looking at, we have an titanium oxide as well. So again, when it comes to primary magmatic conditions and looking at those calculations, we now have a lot more evidence to support that. Oh, and finally, one more, sorry, 0.7. This one here in the core. So in the core of this zircon grain is a grain of potentially pyrite that's been trapped there. So we have interesting things we can start considering for sulfur saturation within these, the magmas that would have extruded the volcanics. So just to give a kind of a brief idea, which I think I've been doing as we go. So some insights into magmatic conditions, but also magmatic hydrothermal conditions. So first, and this image is just the same as the one that I showed just a second ago, looking at that potential, that chalcopyrite grain. But primary magmatic conditions by proxy of mineral inclusions in zircons is broadly, we're looking at that now. So we see things like quartz, potential ilmenite, feldspars, and all these different mineral signatures in the inclusions. And we see signs of metal enrichment indicated by these sulfur-rich inclusions. So we have that chalcopyrite potential here. Beyond that, what we also are seeing is, so these zircon images across the bottom, we have BSC and then CL response left and right. We are also investigating zircons for potential hydrothermal rims. So these analyses, you can see the dots here, they represent probe spots, and when we were doing the data collection for internal standardization, they came back with really low totals during probe data collection. And so we decided to rerun the sample, or rerun the analyses with an expanded element list. So we wanted to see for potential enrichment in metals or elements that we weren't capturing. And we did notice that in these, so these darker, in the CL response, the darker CL rims, they were enriched in iron, they were enriched in manganese almost consistently, and hafnium is quite enriched in the rims of these. So together those things suggest that they are potentially hydrothermal rims, although because the total is still coming back low, we haven't confirmed the presence of them being water-rich domains, but that's something that we're looking at investigating further. And as I mentioned, a brief, only 2-slide update from the work, the melt inclusion work from St. Mary's University. So this slide was given to me by Jake, and we're looking at just some more zircons from the Swayze area. And so looking at silicate melt inclusions and inclusions observed in zircons. So this is an image from the Swayze and shows the location of where the sample came from. And so this sample that he's showing here, and it's highlighting some potential immiscibility, is from a felsic volcanic clastic flow. There are fragments here outlined. There's some mineralization. There's pyrite, I guess, that was found within the sample. And so the sample came from an area that's has subeconomic VMS mineralization, so we'll say it is not endowed, and it's a felsic volcaniclastic flow. These are some of the zircons that were extracted from it. So compared to what I've just been showing, some of the more classic oscillatory zoned things you'd expect to see from magmatic zircon. It's showing a fairly complicated geochron history, is probably all I'll say about it, with potential for Tisdale, porcupine, inheritance. There's a lot of information for that to still kind of, I think, work out. But what's interesting from the melt inclusion perspective is looking at, here we have a transmitted light zircon, and it shows right in here silicate melts that are entrapped in the same zircon that have sulfide melts entrapped. And these sulfide melts are actually metal poor. So it's showing immiscible metal poor sulfide and silicate melt entrapped in the same zircon. And so that will become important, I think, in their discussion for pre-alcesis overall, which, if I move to the pre-al slide, then a brief update on sort of how they're using some of this melt inclusion data is looking, here we have some melt inclusions from the Laurent Penna and the Bousquet Formation. So these are silicate melt inclusions. And within those, in these images, they've highlighted sulfides that have been observed. There are silicate melt inclusions entrapped proximal to galena, so more sulfides, apatite. And what they're noting here is that the presence of sulfides in melt inclusions, it indicates a sulfide-saturated magma system where metals may have been stored before degassing. So they're kind of exploring this potential degassing story. And looking here in this diagram, we have the oxygen fugacity plotted against temperature, so that's titanium and zircon calculations. And they're looking at four samples across different formations. We have a sample of the green from the Hebecor going towards these blue lower Bousquet samples. And then we have two samples from the upper Bousquet that are these yellow and purple. And so the main takeaway, I think, from what they're trying to show is that the oxygen fugacity going from Hebecor to the lower Bousquet, we see a downward shift, a decrease in the oxygen fugacity. But when we then go from lower Bousquet to the upper Bousquet samples, we see a shift in increasing oxygen fugacity, potentially up into this sulfide destruction zone. So right now their interpretations are considering a shift in oxygen fugacity from lower Bousquet to the upper Bousquet, and it suggests to them that sulfides may have been destroyed due to more oxidizing conditions and therefore releasing metals. And therefore metals may have been added to the VMS system via magmatic degassing, and that's the evidence that they're kind of looking at. So to summarize some kind of more takeaways from my own work, the zircon studies, it's definitely important to avoid inclusions and potentially cryptic inheritance. We don't always necessarily see those bright zircon cores in relating to something that might have been assimilated. So it's worth really investigating those zircon textures. And then applying data filtering protocols is going to be one of my next steps. There's a really great paper by Nie et al. Who does they do a great job of being able to clean the data set up to just look at mantle-derived zircons. And so that, I think, is going to really improve the trends that we're able to see in the mineral chemistry. So broadly, mineral inclusions are characterized by SEM-EDS here, and these inclusions can inform us for our zircon mineral chemistry calculations. So as I mentioned, like titanium and zircon as a temperature calculation, we have now constraints on the activity of titanium and silica based on our mineral observations. And then these mineral inclusions can be used to infer primary magmatic conditions. So observing things like quartz, iron titanium oxides or titanium oxides, sulfides, feldspars, amphibals, and micas, they all directly relate to magmatic conditions related to silica saturation, oxidation state, sulfur saturation, and water saturation. And that being an important part of what we're investigating to understand how VMS endowment and magmatics kind of coincide. So that's all I have for you today. Thank you very much.